next rule. So whatever the rules we have seen, using those rules we can sketch the root locus. The complete root locus we can make it right. So once the root locus is available, we need to do some analysis, and to do the analysis, sometimes you need to find the k value at any point on the root locus. So if you have, for example, this is a root locus, and in this root locus, and this is one point on the root locus, I want to find what is the k value at that particular point, because root locus is basically the locus of closed loop poles or roots of the characteristic equation when this k value is varying from 0 to infinity. That means at any point on the root locus you will have some or other k value. So that k value we need to find, and using the rules, whatever the graph you draw, whatever the root locus you draw, that is approximate draw. Especially when you are drawing on the complex plane, it is approximate, it is not scale to that exact scale, so it is approximate. So whatever you draw on the real, that will be accuracy, it is accurate only. So real axis root locus will be accurate, but complex you will have some approximation. Now we need to find the k value. Right, how to find the k value at any point on the root locus? There is one rule available using the root locus graph itself, because assume that root locus is drawn on the graph sheet, and from that you can find out. So let us take one example, like I have k into s plus 4 by s into s plus 2. So for this example, you will have poles and zeros. Let us say I have one pole here and another pole and another 0. Now this particular problem, then what I can do, you will have root locus like this. We will see how to draw the root locus for this problem. There are two poles, and in between root locus area there will be one break point, and there is 1 0. Therefore left to this you have root locus area, there will be one break in point, breakaway point, break in point. So you will have like this, and there is a circle like this, and they come and join in here, and one will go towards 0, the other will go towards infinity. This will be the your root locus, a complete root locus for this problem. Now, so when you draw this, I am taking one point here, and at this point I want to know what is the k value. At what k value my one of the root will be here. So what I can do is, let that point is p. That point is p. From that point you draw the vectors, as like when you are calculating departure arrival, how do you draw the vectors? We draw the vectors from the point to all other poles and zeros. Now in this case we are not going to measure the angles, we are going to measure the lengths. What is the vector length if you have the complete graph sheet? Now take the scale, you measure the length, and before that you just name the vectors. Let us take this vector is LP1, and this vector is LP2, and the other vector is LP3. That means from this point to the first pole, origin pole is LP1, and at -2 is LP2, and from -4, that is 0, is there LZ1. Then what is the formula? The formula is k is equal to pi LP divided by pi LZ. What is pi means? It is a product. So product of all the vectors from all other poles to the point, and this phi z, phi LZ is the product of all vector lengths from all other zeros of GH of S to the point, because point I am giving, right, to the point you draw all the vectors to the zeros, you get the product of it. So if at all, if there are no zeros, then this pi LZ is going to be 1, don't take it as a 0. So this denominator will be 1, so you will have only numerator vectors. So for this problem it is going to be k is equal to LP1, then LP2 divided by LZ1. Then if you have the values, then you can easily substitute, you can get what is the k value. So this k value we can obtain other way also analytically, using your magnitude condition. What is that? Magnitude of GH of S is equal to 1. Take the magnitude of this, substitute the point S here and equate it to 1, because when you are adding magnitude condition there will be variable k. This completely equal to 1, you will find the k value. So this way also you can find out the k value. If the graph is available, then we use the formula k is equal to all the product lengths of poles to the point where you want to calculate k divided by product lengths of all vector lengths of complex all other zeros to the point where you want to find the k. So you take these two ratios, that will be the k value. We can see some examples to draw the root locus diagram. Now, so all these steps are based on the rules given by the events only. So step 1, you just identify the poles and zeros from the open loop transfer function and locate poles and zeros on S-plane. This is the step number 1. We know that in any root locus problem, we want the open loop transfer function GH of S, and this GH of S must be in pole zero form of transfer function. So if you are given directly GH of S in pole zero form, we will take that as it is, or sometimes characteristic equation will be given to you. So once the characteristic equation is given, then you should write in the form of 1 place GH is equal 0, rewrite that and take the only GH of S part, that is the open loop transfer function. But when you are doing this, make sure that the variable parameter k must be in the numerator. If any other parameter, if you have t parameter, a parameter, any other parameter you have, that variable parameter must be in the numerator. That care we should take when you are rewriting in GH of S open loop transfer function. Third case is you will be given the closed loop transfer function. If the closed loop transfer function is given, find the open loop transfer function by assuming unity feedback. We know the formula is G is equal to T by 1 minus T. So T is the closed loop transfer function and G is the open loop transfer function. H is, of course, it is unity feedback of 1. So like this we have 3 possibilities: closed loop transfer function, use this formula, characteristic equation, get the GH of S, well, after writing 1 place GH is 0, ensuring that the k is the numerator, and if GH of S is given directly, if it is in again if it is in time constant form, convert that into pole zero form, and if it is a polynomial also, you can convert that into pole zero form. Ultimately we want a pole zero open loop transfer function with a variable parameter k in the numerator as a open loop gain k. Right. So now S-plane is available. In this S-plane we are going to locate poles and zeros of my open loop transfer function. Step 2. In step 2 we are going to locate your root locus area in S-plane. So what is a root locus area in S-plane? We know the method to find out the root locus area in S-plane. So S-plane, that to be in the real axis, not the complex, only on the real axis. So look at the real axis, we have pole zero locations available, and depending upon the rule that is given by events, then you can draw you can identify the area. So while identifying the area, we have the different color here, then we write some hashes like this. Wherever the root locus area is there, we draw small hashes like this. So this is the root locus area. That means when you draw the complete root locus sketch, and you must take only the root locus in this area on a real axis. This is step 2. What is step 3? In step 3, we are going to get the complete information of the asymptotes. What is asymptote? Asymptote is an imaginary straight line which will guide one of the root locus branches to reach infinity. Therefore, and how you will get the asymptotes? If P is greater than Z, then you will get asymptotes. P is equal to Z, where P is open loop poles, Z is number of open loop poles, Z is number of open loop zeros. So if these two are equal, asymptotes are not needed, this step is not needed. Simply write, since A is equal to 0, no asymptotes at all. So for example, if P is greater than Z, yes, there are asymptotes. So when asymptotes are there, then you find out the centroid. What is centroid formula? We know the sigma poles minus sigma zeros divided by P minus Z. So in this way you can find out centroid. Then what are the angle of asymptotes? So to find angle of asymptotes, we know that when A is equal to 0, no angles at all. When A is equal to 1, yes, your theta 1 is equal to minus 180 directly. When A is 2, theta 1 is minus 90, theta 2 is minus 270. When A is 3, theta 1 is minus 60, theta 2 is minus 180, theta 3 is minus 300. Again, when A is 4, also we can have 4 angles here. Theta 1 is minus 45, theta 2 is minus 135, theta 3 is minus 225 and theta 4 is minus 315. So maximum you will have 4 asymptotes in any problems while you are doing manual calculations. Therefore, you write all asymptotes angles and also have the centroid. You draw asymptotes on the S-plane. So you have already till this step you have poles and zeros on S-plane, and you have root locus area, and also you have centroid, and you have all asymptotes. Next, step 4. So step 4 is breakpoint calculations. So what is breakpoint we know, and there are breakaway and break-in points. You do all the calculations for the given characteristic open loop transfer function, and before calculating you just check the possibilities. If there is any possibility of occurring the breakpoint, you calculate. If there is no possibility of occurring breakpoint, simply say, so there is no possibility of occurring breakpoint, so breakpoint calculation is not needed. So this step is over. Next, coming to step 5, imaginary crossover point calculations. So again same thing, first check the possibilities, then do the calculations of imaginary crossover point, then find out the k value and find out that ICP value, imaginary crossover point values. Step 6. So if you have complex poles or complex zeros, then find out angle of departure and or angle of arrival. If there are no such complex poles or complex zeros, simply say, so no angle of departure and no angle of arrival. So if you have, you should calculate in step 6. Then this is the complete information available till step 6. Now using all the calculated points, calculated values, then we can draw the complete root locus sketch in step 7. In step 7, you have complete root locus diagram for the given system. And step 8, once you have the root locus diagram, that is not end of the story, then we need to analyze the root locus diagram. So to analyze the root locus diagram, then we will do all this analysis part in step 8. Sometimes in the analysis you need to find the k value, therefore there is a rule available to find the k value. So you use the rule and find the k value, whatever the analysis you want, you do in step 8. So if you follow all these step 8, then we can complete the root locus.